Application of the service. The addition, change and deletion of data in a database, however small, must run on a constant frequency. Suppose we double the time gap for one to obtain the full backup data in the form of a magnetic tape from the given database. So we are talking about doubling the time gap. Working with that, in relation to restoration and backup of the database, which of the following is a proper and fit description? Option A is the time required to deal with restoring the system from logged information takes twice as long on average. So we're talking about twice as long on average. Option B says the magnetic tape used for one full backup is about twice the amount. So the tape is twice the amount. Option C says the magnetic tape used for one full backup is about half the amount. So in fact it goes the other way. Or option D says the average time taken to obtain the full backup takes twice as long. Again, we're talking about the average time. In fact, you will have noticed that the question concerns a full backup. First of all, we have to confirm the different types and the methods of backup that are available to us. So first we'll begin by looking at what is a full backup. One method is to back up all the files and folders every time. Since there is no overwriting the data, all the backup data are left, and hence with simple manipulations one can restore the system in a short period of time. This method is suitable for when the size of the data that needs backing up is small. So we're talking about small data. We have a diagram here. Now the first round, all the files that exist at this point in time, and it is the one with the circle here, gets backed up. In round 2, when you have a little bit more data, all the files that exist in this point in time, again, get backed up. So you're copying the first set of data as well in your second round of backup. And again, when you have more data in your third round, you've got 3 lots of data here, you back them all up also. So each time, each round of backup, you fully back up. You do not overwrite data. All the backup data are left. So it's to back up all the files and folders every time. That is what a full backup is. Now there is another method which is known as the incremental backup. Now in this method, a system backs up files that has been changed since the last incremental backup. Even though this method takes the shortest amount of time to back up, it also takes the longest time to restore. So in this method, the system backs up only the files that have changed since the last incremental backup. Now this is suitable in situations where there are a large amount of files that need backing up. So we're talking about a large amount of files. To minimize the disk domain consumed, it's also suitable when we have frequent backups. Again, frequent. Now we have a simple diagram to help us understand what's going on here. We have the original data on the left here and the backup data. Now in the first round you have the first original set of data that you have, and you just copy, because that's the only data that you have and it's the first round, you just copy the entire load to the backup. Now as we go to the second round, and remember that this is the time axis going down, so we have time going down. At some later time we'll have the second round, and because time has progressed we've got a bit more information here. We've got another load of information here, which is signified by the 2. What we would do in the full backup would be to just take the entire thing, but in the incremental backup what happens is only the extra information, only the new data gets backed up, because you already have a copy of the 1 somewhere in the backup. So you only copy over the extra part. Again, you have some time after, in the third round when you want to back up, we will have a bit more data. Again, here this would be the new one in this stage. But although we have a huge amount of data here, we already have 1 and 2 backed up somewhere in the data, so we only take this new chunk, the 3. So then we copy the 3, and again it would be the same for the 4. So that over time, you've got backup of the entire system, the entire picture that you can see in the 4th round. All the pieces are there. If you want to back up from your backup data, all you have to do is to stitch these pieces of data again back together. The problem is that makes the process take a long time to restore. Now there is another method which is known as the differential backup. This method of backing up only saves the data that has been changed since the last full backup. And the keyword is the last full backup. That's how it makes it different from the incremental backup, where the incremental backup saves the data that has been changed since the last incremental backup. In the differential backup, it only saves the data that has been changed since the last full backup. Now, one of the merits of this method is that compared to a full backup and incremental backup, the time for restoration is shorter. Now, that is an advantage of the differential backup. If one continuously employs differential backup frequently, the size of differential backup in comparison to a full backup could potentially be enlarged. As this method only saves the data that has been changed since the last full backup, in comparison to a full backup, the time taken on disk space used is less. And in comparison to the full backup incremental backup combination, this differential backup method is more efficient. With regards to restoration, concerning only the latest full backup plus last differential backup, this method is simpler than the incremental backup. Now again we have a diagram of the backup history here. First of all, let us begin with the first round, where we have one chunk of the original data. We will back up this data so we have an exact copy, and this of course is a full backup. Now in the second round, what we have done in the first round is a full backup. So when we are backing up in the second round using the differential backup method, it backs up the data that is different from the last full backup. Now this load of the data is from the last full backup, which means that this is the new piece of data, which means that this is the only part that gets backed up. Now in the third round, you can see that we have two new chunks here. Again, the last full backup only concerned chunk 1, which means that any part that is not chunk 1 is what gets saved in the third round, which of course is this 2 and 3, and that gets saved into the backup, and the same for the fourth round. In each case, the most recent full backup is going to be the backup from first round, which is the original data, so that at each point it backs up the new piece of information with respect to the last full backup. Now let us get back to the question. The question said that we are going to double the time gap for one to obtain the full backup data in the form of magnetic tape from the given database. Now, in order to answer this question, we'll look at two different cases, hypothetical cases. So first of all, we're going to suppose that a full backup takes place every single week. In the second scenario, we're going to then, after that, consider a full backup happening every 2 weeks instead. So first of all, let us have a look at the first picture, that a full backup takes place every single week. So first of all, we have the original database. Then we have a 1 week of adding and changing and deleting the data to form DB1. That gets backed up. That is your first week from the beginning. So we have DB1, backup file 1. And then another week passes of adding and changing and deleting. And then we are here with DB2, which gets fully backed up. And then we have another week and get a backup of DB3. And then in the final 1 week with DB4, we see that an error happens. Now in this case, if the error occurs in week 4, before the backup of DB4 is created, DB3, which has been changed just before, is restored. So we are left with DB3. The journal information is confirmed. Logged file 1 week's worth of edited content has been added to DB3 and DB4 is restored. Now let us have a look at the scenario when we do a full backup every 2 weeks. So first of all, we are here with the original database, and we have 2 weeks of adding and changing and deleting data, where we are left with DB1. And we perform a full backup of DB1 after 2 weeks, and then we have another 2 weeks of adding and changing and deleting data, where we are left with DB2, and an error occurs. Now, in this case, in week 4, when the error occurs, we can only restore from DB1, which has been changed just before. The journal information is confirmed, and 2 weeks worth of edited content has to be added to DB1, and then we get DB2 restored. But in this case, we have to add 2 weeks worth of edited content, rather than earlier when we had 1 week's worth of edited content. Now, looking at the available choices for the answers, there is A, which concerns the time required to run a restoration with regards to journal information, and B to D, which concern full backups. Now firstly, let's look at the last 3 options, B, C, and D, about full backups. The required disk space of a magnetic tape and time necessary for a full backup are roughly in direct proportion to the database capacity at the time of the full backup acquisition. In the question, it says the addition, change, and deletion of data in a new database, however small, must run on a constant frequency. The database capacity would change at that point in time. The fact that the chance is small would mean that one could think of it as not really changing. Hence, even if the time taken to obtain the backup takes twice as long, it would be hard for one to imagine the data doubling or being halved within this period of time. Therefore, we see, logically, that B, C, and D are not applicable answers to our question. Now, finally, to complete the picture, we'll look at option A, which concerns itself with the time required for restoration. Magnetic disk as a medium obstacle in a situation whereby the content of the database disappears. First, the latest backup files would be used and the content would be restored up to that point in time. After that, the journal information would be used and the edited content after the latest backup could then be restored. At times like that, the time required to process the restoration is in direct proportion to the amount of journal information there is between the latest backup until the point of the error. With this, the journal information must have happened at a constant frequency, and hence lengthier the time between the latest backup and the error, and this is the important thing, the lengthier the time between the latest backup and the error, the longer time it would take to restore the system. And therefore, if the time required to obtain the backup is doubled, the amount of journal information is also doubled, which would in turn mean that for the purposes of restoration, the time would also be doubled in average. So A is the correct answer.